For this video, we're going to talk about sets of numbers, and what you see here in front of you is a diagram that pretty much describes how real numbers are, or the different types of real numbers, I should say. So everything inside of this rectangle is considered a real number. And we have a fancy R right here, which if we're using different types of mathematical notation, this R tells us that it is a real number. Now inside the set of real numbers, we have two subsets. Rational numbers over here, which is used or denoted by the letter Q, and irrational numbers, which don't have their own little special letter to denote them. They're just called irrational numbers. Now, to make the most sense of our rational numbers, let's start at the innermost circle here, which is natural numbers. These are the numbers that you have been working with since you learned how to count. They are 1, 2, 3, 4, 5, 10, 12. They're a number that does not have a decimal. They're just natural numbers, numbers you can count. Then, from here, if we add the number 0, we have the group that is known as whole numbers. Whole numbers include natural numbers, but they also include that number 0. So this is pretty much if you had a number line, draw a number line here. If I have 0 right here, and let's put a little dot at 0 and say that I am going this direction, this is the set of whole numbers. Okay, so it is everything that is 0 or bigger, as long as it is a whole number. We aren't dealing with these spaces in between our little dashes yet. We are just dealing with the dashes themselves. So those are whole numbers. If we were to start including everything that goes to the left of the 0, well, that is considered an integer. Negative numbers, still no decimals or fractions, just the numbers themselves. So if I had -1, -2, and so forth, these are considered integers. And then finally, the last part of real numbers is our rational numbers. These are your decimals, or your fractions, or mixed numbers. They are even your decimals that have repeating elements to them. So that makes up everything inside of our number line, pretty much. Irrational numbers are numbers that don't have a pattern. So like the square root of 2, if you were to type that in on your calculator, you would get a number that doesn't repeat like we see in this decimal. It's irrational. It can also be pi, which is 3.14159, so forth and so on. It continues on forever. Same thing with the letter E. That number continues on forever, and so forth and so on. So if you see a square root and it's not a perfect square underneath, it's an irrational number. So if I had square root of 5, that's irrational. If I had the square root of 9, however, well, the square root of 9 is 3, and that is a natural number. All right, let's move on to the next little piece of this video. All right, continuing on, we see some definitions here for some vocab terms. We have the word set. A set is a collection of items called elements. And basically, the elements are your numbers, your different types of real numbers that we just discussed in the first part. And a set is how they are organized. Now, as it says down here, a set is a list of numbers, the elements. A subset is a smaller list of numbers from a bigger set. So let's say that I have a set over here. Let's just say that's 1, 2, 4, 8, 12. I have a set of natural numbers here. Now, I could say, oh, instead of having this big set right here, I'm going to make a subset. And that subset could consist of just 1, 2, and 4. It's its own little set that is part of this bigger set. Okay? And then the last piece we have over here is something called an empty set. That's basically like a circle with nothing on the inside. It is also denoted as this symbol. That is the empty set. There are no elements and no numbers inside the empty set. Now for this first example we have here, we are given, we are given a set of numbers. The set of numbers consists of -2, pi, -0.321, 3/2, and -√3. First part says, order the numbers from least to greatest. This is something you've been doing in math for years and years and years. Smallest number first, work your way to the biggest number. But the catch is here, you've got an integer, something that isn't an integer, another non-integer, a fraction, not an integer, and -√3, also not an integer. And the reason why I'm not telling what all of those are to start off with is because that's part B. Classifies each number by the subsets of the real numbers to which it belongs. So if we're going to order these from least to greatest, we should probably make these numbers something that we can actually order. And to do that, we want to turn them into a decimal. Whether it's pi or the -√3, we're going to use a decimal approximation just to help us. Now, -2 can stay -2. Pi is 3.14, and we're just going to stop at 2 decimals. We don't need to go further. Then we already have a decimal here, -0.321. 3/2 is the decimal 1.5. You get that by dividing 3 into 2 pieces, 1½ each. And then -√3. That's the one that we're not going to know off the top of our head. So if we type it into our calculator, we end up with -1.73. And now that we have all of their decimal equivalents, we can easily order these from least to greatest. Take a look at the numbers that we have. What's the smallest number? It's -2. What's the next smallest number? Well, our next smallest decimal is -1.73, which is the equivalent of -√3. So we'll say that our next number is -√3. When you're creating your list, please don't use the decimal equivalents. Use the actual number you were given. Okay, next smallest is -0.321. Then we've got 1.5. And lastly is 3.14, which we know is pi. And there is our order from least to greatest. Next part says, what's the classification of these? What type of real numbers are each of these elements? We've got -2, which, since it's negative, it is in the integer family. We have pi, which we saw earlier as an irrational number. We have -0.321, which is a decimal. It does not repeat, so this is a rational number. We have 3/2, which, even though it's a fraction, it's still a decimal, which, now that I see that, I made a mistake in my ordering. 1.5 should not have been 1.5. I should have written it as 3/2. Sorry about that. And then lastly, we have -√3, which, you have a square root. It's not a perfect square underneath. It's an irrational number as well. All right, so we've talked a lot about our different types of subsets of real numbers. Now let's talk about some ways that we can categorize numbers into sets and different types of notation for that. One of the first ways that we can represent a set is through what is called roster notation. And this name pretty much describes what you're doing. If you think of a baseball roster or a team roster, what are you doing? You are listing every single person on the team. My class roster lists every single person in the class. So a roster notation using braces right here, as you can see, it lists everything that is inside the set. So if I'm using a word notation here, numbers between 1 and 10, here is the roster notation of that set. Brace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, closing brace. Placements in Kentucky Derby results. There are 21 horses in the Kentucky Derby. So we have brace, 1 through 21, all listed, and then closing brace. So roster notation is pretty simple as long as we know what is inside of our set. And these are called finite sets because there is a finite number or a countable number of elements inside the set. What do you think the sets would be called if there's too many to count? That would be an infinite. An infinite set. And you wouldn't want to use roster notation for an infinite set because you'd never end. You would constantly be writing numbers because they wouldn't stop. It goes on forever, just like infinity. So roster notation is good if we have countable numbers like we see here. But if we don't have countable numbers, we have a couple other types of notation that we can use. Another type of notation is called interval notation. And this kind of fixes the problem when we have an infinite number of possible elements inside of our set. This is what interval notation looks like, and this is what it looks like as a number line. We see that we have an open circle on 3 and 5. We are worried about the numbers in between 3 and 5 as shown to us by this inequality. And instead of writing all of this, we could use interval notation. A couple things to remember or notice about interval notation. If you see the less than sign, the greater than sign, either of those, you are going to use a parentheses, depending on which direction. If you are talking about the first number, which is less than, you're going to use an open parentheses. If you talk about a second number, which is not included, you're going to use the close parentheses. But if you see less than or equal to, or greater than or equal to, you are not going to use parentheses. Parentheses mean that that number next to it is not included. You want to use a bracket or a brace. I think in this term it's called a bracket, so we'll use a bracket for opening and closing. Now, here we see 2 parentheses, so 3 and 5 are not included. If I were to make a number line, like we see here, and I had an open circle at 3, a closed circle at 5, and I was going in between them, I would write this in interval notation as open parentheses 3, comma 5, close bracket. Because we can have a mix of them. It all depends on what we see here. The 3 is not included because it's an open circle. We use a parentheses. The 5 is included because it's a closed circle. We use a bracket. All right, and we have another type of notation coming up next, which I prefer interval notation, but I'm trying to give you options that you can use. I don't care which method you use. But if the homework or I ask you on a test or a quiz to use a specific type, please make sure that you are aware of these specific types. So let's look at the next one. The last type of notation we're going to talk about in this lesson is called set builder notation. And this is probably the most complicated one. This is an example of a set builder notation over here. And what it really is just a way to take this big long sentence, the set of all numbers x, such that x has the given properties of whatever, and here it says, okay, we have x, that's our variable. If you were using y or a different letter, you would put that here. This little line just means such that. And then this is whatever property it's asking you to use. So here it says 8 is less than x is less than or equal to 15. So we don't include the 8, we include the 15. And it says x is part of the natural numbers, meaning there aren't going to be any decimals or fractions. This is a finite set. And all this explains here is this set right here. 9, 10, 11, 12, 13, 14, 15. This all fits into 8 is less than x is less than or equal to 15, and x is natural numbers. That's set builder notation. It's the most complicated. You're going to see some of these examples on your homework. It'll ask for set builder notation specifically. So we got to do a little bit of practicing with it. But if you don't want to use this in the future, you'll more than likely be okay with that. And that's all I have for us today in this video. It's gotten kind of long, longer than they will normally be, so I apologize for that. But hopefully you found this useful, and if you needed to review this first lesson, you took a look at this. Good luck.